A very warm welcome. हाइड्रोकार्बन्स के सॉल्यूशंस का डिस्कशन करेंगे, एनसीईआरटी क्वेश्चंस के सॉल्यूशंस का डिस्कशन करेंगे हम अपने इस सेशन में। तैयार हैं आप? तो चलिए शुरुआत करते हैं। यूटिलिटी क्या है, लेकिन ध्यान रखिएगा हमारे सॉल्यूशंस के डिस्कशन एक एवरेज सॉल्यूशन की तरह नहीं है जिसमें हमने कुछ भी इधर से कॉपी पेस्ट कर दिया है। कोशिश इन सॉल्यूशंस की ये है कि इनके डिस्कशन के माध्यम से थ्योरी भी आपकी पूरी रिवाइज हो जाए और वो जो कॉमन पॉइंट्स हैं कंफ्यूजन के वो भी लगातार आपके क्लियर होते जाएं। एंड दैट इज समथिंग व्हिच इज वेरी वेरी रिमार्केबल अबाउट दीज सॉल्यूशंस, राइट? सो लेट्स बिगिन Unit 13 Hydrocarbons of 11th standard NCERT chemistry. This is Shishir Mittal from Vyas EDIFICATION. The first question: how do you account for the formation of ethane during chlorination of methane? Wow. We are conducting a chlorination of methane, then please remember the first point you mention is that the mechanism. The mechanism is free radical mechanism. So you should first write down that mechanism is free radical mechanism, right? And free radical mechanism takes place in 3 steps. 3. Number first, initiation, when free radicals are generated, maybe by shining light or by heat or whatever mechanism. Sometimes people add catalysts like peroxides, but we manage to generate free radicals as the initiators. Second step is propagation, the most important. In propagation step, something which keeps on happening throughout the main body of the reaction, there are 2 reactions which happen. The first one, when you have methane, it reacts with chlorine free radical. It abstracts, it takes away one hydrogen atom. What happens is CH3H, this H gets connected to Cl. As Cl approaches hydrogen, partially it forms a bond with hydrogen and partially the bond of hydrogen with methane begins to break. And ultimately what happens is hydrogen is taken away by Cl because Cl loves to form a good bond with it, and I'm left with only methyl radical. In the second step, methyl radical again reacts with chlorine to give you CH3Cl and it regenerates. It gives back the original Cl radical, and this Cl radical again goes and hunts up another methane molecule, again eats it away, again generates new methyl radical, and this is the cycle which continues, right? So this Cl can again go back here with another methane, and thousands and hundreds of thousands of molecules are actually converted. Hundreds and thousands of molecules are actually converted before a Cl radical actually gets exhausted or terminated, which is again the third step and the last step of radical mechanism. First and last step are not really the ones which we are concerned with in this question. But the fun part is this. Note that methyl radical is generated in propagation, right? And then what happens? During termination reactions, there is a probability that 2 methyl radicals may just come across each other. 2 methyl radicals may just come across each other, and the moment they face each other, lovingly they can form a bond. All they lack is a simple bond, and this simple, nice, happy bond, the moment this bond is formed, what do you get? You get ethane. That's it, you get ethane like this. And this is how ethane is generated during free radical halogenation or chlorination of methane. By termination involving only methyl radicals, this is what we get. And that is, my dears, the answer to our question. This is the mechanism of formation of ethane during chlorination of methane. Write IUPAC names of the following compounds. Wow. We have CH3, CH double bond C, CH3. hold twice, CH3CH, CH3CH, double bond C, CH3CH3. Let me draw the bond line notation so that naming becomes easier, and let me again invite you to recall the rules of nomenclature, because as I suggested, these are not simply answers which we are presenting to you, but also the methods, and using these questions as excuse, we will again make you revise the essential theory. So what are the rules? The rules say that first of all, you are supposed to choose the longest possible carbon chain. Now, 1, 2, 3, 4, 5. 1, 2, 3, 4. 1, 2, 3, 4, 5. CH2 double bond C. I'm sorry. I'll just draw this again. Double bond CH, C, 1, 2, 3. Triple bond C. And then I have CH3. A molecule like this, and this is already a bond line notation. Now what do? I choose the longest possible carbon chain. Well, that would be 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. Whichever case you take, that chain looks like this only. Okay. Now from which end should I begin to count? Having chosen the correct possible carbon, longest possible carbon chain, every chain has two ends, and I have to start giving numbers from one end, 1, 2, 3, 4, or opposite 1, 2, 3, 4. Let me try 1, 2, 3, 4. This is one way of numbering it, the black way, and there could be, well, a red way. Red way is 1, 2, 3, 4. What is correct? The second rule says, are there double or triple bonds? Check. Yes, there are. If there are double or triple bonds, then you must choose them in such a way, you must number them in such a way that the double or triple bond gets the lowest possible locant or number. The black side, 1, 2, the double bond gets number 2. And the red numbering, 1, 2, again the double bond gets numbering 2. So whether I count it from this end or that end, double bond again gets a number 2 only, so it appears like 2-butene always. Is there any other rule? Yes, then there is a third rule, which says that if first and second points are the same, then look at the branching. Whichever side has earliest branching or earliest substituent or earliest point of difference, choose that. The earliest point of difference, if you say 1, 2 and there's a branch, 1, 2 and there is no branch. On the black side, there is a branch of methyl at 2. In the red numbering, there is no branch at 2. So black is better as compared to red. So I would say that no, that red numbering is not as good. I'll just get rid of that. The black numbering, the black is beautiful, of course. We will just write it down. 2 methyl butene. 2 methyl butene. Why bute? 4 carbons. So root is bute. Alkene, that is why ene. Alkene appears on number 2, that is why butene. 2-methyl butene, and that is, my dears, the IUPAC name of this lovely compound. What about this one? Actually, there is only one chain. So there is no confusion when it comes to selecting the chain. From which side should I number? From this side or that side? Whichever has earliest appearance of multiple bonds, that side should be chosen. So 1, 2, 3, 4 and 5. This is, my dears, the way we choose it. And then 1, 2, 3, 4, 5. Now this is 5 means penta. Yeah, pent. So this is pentenine, ene and ine. So this is pent 1 ene 3 ine. Pent 1N 3 ine. This, my dears, is the way we write it. C. What is the longest possible carbon chain? Well, this seems to be the only carbon chain. 1, 2, 3, 4. It is same both the ways. So it is butadiene. Why there are two alkenes? So di-ene, the butadiene. But alkene happens at 1 and 3, so 1, 3, butadiene or buta 1, 3, diene. Both are correct. You can write it whichever way you like. 1,3-butadiene or buta 1,3-diene. All, either of them is of course the correct number. Then D. Oh my God, what should I do? Well, carbon chain can well be chosen. 1, 2, 3, 4. And then what do I say? I would say this is butene, yes. The 4-phenyl, because this group is called phenyl. This is phenyl. 4-phenyl but 1-ene. 4-phenyl but 1-ene. Phenyl group can be very conveniently chosen as a substituent. So, don't be impressed by the fact that this is a ring and there are 3 pi bonds. It's okay, it's there, very nice, but this is as well as, a very good name. What about this? In this case, there are 2 substituents on the benzene ring, so benzene ring should be chosen as, please remember this is benzene, don't call it 1,3,5 cyclohexatriene. It is actually benzene, it has a special status, 1 and 2. Wow. So what is this? I hope you can see this 1 and 2. 2-methyl benzene 1-ol. Benzenol, yes. Or if you want to be stylish, you could also write it as 2-methyl phenol. Why? Benzene 1-ol is also called phenol. So, a very accurate IUPAC name is this. But as a minor possibility, 2-methyl phenol, this also could have been the name, or even if you stoop down to a common name, O-cresol. What are cresols? Cresols are molecules in which on one benzene ring there is one methyl group and one OH group. And if they are adjacent to each other, it is called O-cresol. 1, 3, M-cresol and 1, 4, P-cresol. But that, my dears, is a common name. That is not, of course, the IUPAC name. This is just a common name, albeit a very popular common name. What about the next ones? Let's take a look. Oh my God, what is this? Let's draw bond line notation and then let's take a look. CH3, CH2 whole 4 times. 1, 2, 3, 4. 1, 2, 3, 4. So I have methyl and 4 methylene groups. And then I have CH. And that group now divides into 2 portions. I have CH2, CH2, CH2 3 times and then methyl. CH then CH2, 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 CH3. CH2, 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 CH3. This is that carbon we are talking about. This one. Right? What about this? CH2. Then again I have CH. Then I have CH3, CH3. Oh my God, so ugly. Whatever. Just check it once again so that you are sure that you have not made any mistake. CH3, fine. And then you have 4 CH2. 1, 2, 3, 4 CH2. And then you have CH with a dot. CH with a dot. I've just put a heavy dot so that you can, reconcile and check. Otherwise, this heavy dot is not needed as a part of standard IUPAC stuff. We just have to name it. Also, what is the longest possible carbon chain? Well, very clearly, this looks like the longest possible carbon chain. Yes. This dotted line is not very nice. I'll just, I'm trying to change it over to a highlighter. Let's see. Longest possible carbon chain. I'm just trying to highlight that for you. Yes, I think this is much cleaner. Yeah, I like it. So, this is the longest possible chain. How do we number it? We start numbering it from the side wherever earlier branch appears. 1. If I count it from here, 1, from here 1. 2, 3, no branch. 4, no branch. 5, there's a branch. This side, there is a branch on 5 number. If I count from this side on 5 number, there is no branch. If I count from this side on 5 number, there is a branch. So accordingly, I must say, numbering must begin like 1, okay, and then 2, 3, 4, 5, 6, 7, 8, 9. Oh my God, there are 10 carbon atoms. This is decane. Yes. Which group is this, by the way? If you just care to see 1, 2, 3, 4, there are 4 carbon atoms and the ending is branched. This is isobutyl group. Wow, this is isobutyl? Yes, this is isobutyl. Now, how do I write this? I'll just write the name. We'll write it. Let's do that. So, this is 5 isobutyl decane. 5 isobutyl decane. That's it. That's it. That's the name. If you're not happy with this, there is another method. If you don't want to use these common names accepted in IUPAC, there is a method of side chain nomenclature. See, this is the side chain. If you care to note, this is a side chain. Yes, quite true. Very stark indeed. Now, this atom which is attached to the main chain, this atom which is attached to the main chain, we will say this is 1 dash, 2 dash, 3 dash. That means this side chain will be named as propyl. Okay. So instead of isobutyl, I can call it 2-methyl propyl. So 2-methyl propyl. Why do you put dash? Just to make sure that we highlight the fact that this numbering is not the main chain but the side chain numbering. And this entire group is present on number 5. So you can call it like this. 5 2 dash methyl propyl. And the entire thing is what? The entire thing is decane. So that it should be called decane. I don't like dashes if you say. Then there is a third offering also by IUPAC. They say you can put this in bracket 5 2 methyl propyl decane. If you are enclosing the side chain in a bracket, then you don't have to use dashes. The moment you are numbering within brackets, it means that it is the numbering of side chain. So 1 or 2 or 3, each of them is the correct IUPAC name. Don't you forget. And let's look at G. Oh my God. This is so heavy. I have enormous carbon chain. And needless to say, this carbon chain itself would be the parent carbon chain. This, my dears, would be the main chain. If this is the main chain, from which end should I begin to number? 1, 2, there is a double bond. 1, there is a double bond. Whichever side gives you earliest double bond, from that side you must number. In that case, we are really not worried about the side chains. The higher priority is taken by the double bonds. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It is again decane. It's not ane. 1, 2, 3 double bonds. So this is trine, decatrine. Deca 1, 5, 8. 8 trine. It is decatrine, but there is a side chain, there is ethyl. So this is 4 ethyl. 4 ethyl deca 158 trine. That's it. For the following compounds, write structural formulae and IUPAC names for all possible isomers having the number of double or triple bonds as indicated. Well, we will first write down all the possible isomers and then we will name them also. If we have a formula C4H8 and we have only one double bond, how many different structures do you think we can draw? Well, we would be able to draw. C4H8 means CnH2n. So this looks like an alkene, yes. So I could have had, first of all, let me, try to draw the possible structures. Or what is it? What are you drawing? See, there are two possible structures. One is N-butane, only the carbon skeleton without double bonds. And the other one is isobutane. And in how many different ways can I put a double bond on them? I could have put a double bond here. That would make us 1-butene. I also could have put a double bond here. That would have been but2ene. Right? They are the same two butenes. Yes, they are. But there is a subtle difference. What? In this case, if you see, H and methyl are on one side of double bond, and both the methyl groups, if you check, they are on the opposite sides of double bond. Such a thing is called trans. Trans 2-butene or trans but2ene. On the other hand, if both the methyl groups are on same side, this will be called cis 2-butene or cis but2ene. So yes, there is a difference between cis and trans also. So these are also possible. So 3 butenes, 1 butene, and there are two possibilities for 2 butenes, cis as well as trans. This or this. I could put a double bond anywhere actually. If I put it here, fine. Do you see? It is same as this and it would be same as that. So there is no need for a separate structure here. I can just survive with one structure, and this is the famous isobutylene or 1,2,3 2-methyl propene. This is the IUPAC name, or we could simply say isobutylene, but isobutylene is the common name. This is not IUPAC name. We were asked IUPAC names, so let's just stick to 2-methyl propene. What about C5H8 with one triple bond? My, there's going to be a triple bond, yes. So first let me draw the skeletons. 1, 2, 3, 4, 5 carbons. 1, 2, 3, 4, 5 carbons. And 1, 2, 3, 4. There are 5 pentanes possible. Normal pentane, isopentane and neopentane. And now I am supposed to actually mark or put a triple bond anywhere. In how many different ways can I put that triple bond? I could do it here, I could do it here. What is this? This is 1 pentyne. And there is 2 pentyne. And that's it. Now some of you may say, no, sir, there is most possible. You could write this also. This is 3 pentyne. No. 1, 2, 3, 4, 5. This is same. There is nothing new. So I don't have to count this separately. Not required. So I have 1 pentyne and I have 2 pentyne. And what about this? Could I put a triple bond here? Yes. Could I put a triple bond here? No. Why? 1, 2, 3, 4, 5. Now carbon possibly cannot make 5 bonds. That is preposterous. That's totally wrong. No. Is this correct? Yes. What do I write? 1, 3-methyl but 1 ion. This is the structure. 3-methyl but 1 ion or 3-methyl butane. Either way it is correct. No problem. Neopentane. Can I put a triple bond anywhere? No. That would exceed. That would be like, carbon is forming 1, 2, 3, 4, 5, 6 bonds, which is not possible. This is absurd. So if I just erase out the absurd possibilities, should I do that? Let me make it look more clean. Let me remove the junk. Yes. If I remove all the nonsensical options, I get 3 isomers, 3 alkynes. And this question talks about ozonolysis. What is ozonolysis? Ozone is O3, gas. And lysis means breaking down. So breaking an organic molecule using ozone is called ozonolysis. And let's see, how can we ozonolyze these compounds? You have pent-2-ene. 1, 2, 3, 4, 5. This is pent-2-ene. On ozonolysis, this is what that happens. You break the double bond. And what do you get? You should write it. Just separate them. Just put them a little far apart. And all you need to do is just attach oxygens here. What? Yes. That's all. Yes, that's all. What is this? You have to write IUPAC name. So this is 1, 2. This is ethanol. And 1, 2, 3. So this is propanol. Sadenal rahoge to whatever. Ethanol and propanol. Now, they have not mentioned whether this is oxidative ozonolysis or reductive. So I must write down the products of both the ozonolysis. If I have reductive ozonolysis, these are the products. In these cases, in case of reductive ozonolysis, what do? You add ozone and then follow it up by adding zinc dust. Then you would get ethanol and propanol, 2 aldehydes as the products. If you don't add a reducing agent like zinc dust, if you just add water, then this becomes oxidative ozonolysis, and in oxidative ozonolysis, the aldehydes, it's not that you will not obtain these aldehydes, but these aldehydes will not stop here. They would be further oxidized to carboxylic acid. So you would get ethanoic acid and you would get propanoic acid. This, my dears, is what you will obtain. Ethanoic and propanoic acids. The second compound in ozonolysis is 3,4-dimethyl hept-3-ene. 1, 2, 3, 4, 5, 6, 7. This is heptane. 1, 2, 3. 3,4-dimethyl hept-3-ene. This is the compound. Can we carry out its ozonolysis? That is very, very simple. You have learnt it. Just break this up. Ding, dang, ding. And just stretch it out a little like this. And then what do you need to do? Just attach O's here. Oh my God, these are ketones. Yes, they are ketones. And let me remind you, ketones are very difficult to oxidize. So maybe oxidative or maybe reductive. In both oxidative and reductive ozonolysis, these are the products only. Same products, there is no difference. Names 1, 2, 3, 4. 1, 2, 3, 4, 5. This is butanone. Or if you want to be stylish, 2-butanone. It is not necessary, but you can write it 2-butanone. And this is 2-pentanone. Why one? Because it is a ketone. We have 2-ethyl but-1-ene. But-1-ene and this 2-ethyl. Ethyl. Again, very simple. What do? cut off the head like this. So I would obtain this and this. What is this? If I have reductive ozonolysis, I would obtain methanol or formaldehyde. This is CH2CO. Yeah, sorry, CH2 double bond O. And this is an aldehyde, of course. And this is, sorry, pentane 3-pentanone. Okay. And what about oxidative? If it is oxidative, please remember 3-pentanone stays as it is. But if you have formaldehyde, formaldehyde is very easily oxidized to formic acid. And usually acids are very difficult to oxidize. But there are two acids, two carboxylic acids, which can be oxidized further. If I have HCOOH, formic acid, it gets oxidized to carbon dioxide. And if I have oxalic acid, H2C2O4, oxalic acid also gets oxidized to the normally acetic acid or ethanoic, propanoic, butanoic. All these acids stay very well as the products in oxidative ozonolysis, except two acids, 1 and 2. Formic and oxalic acids are oxidized to CO2. Now you may say that there is no oxalic acid here. I know there is no oxalic acid here, of course. This is extra information. It is not relevant in this question, but it may come handy in some other question. So in this case, you get 3-pentanone and CO2, and that very well is an exhaustive answer for this question. Write the IUPAC names of the products obtained by the ozonolysis of the following compounds. What do we have? We have 1-phenyl-but-1-ene. Now 1-phenyl-but-1-ene. What does that look like? 1-phenyl-but-1-ene, like this. 1, 2, 3, 4. How much is this? If you ozonolize this, what do you get? Well, we have this is what we get, my dears. This, of course, is a product of reductive ozonolysis. This is benzaldehyde, yeah, or IUPAC name would be benzene carbaldehyde. And this, of course, is 1, 2, 3. So this is propanal. Of course, these are the products of reductive ozonolysis. No, we want this to be oxidative. Well, let's do it again. If you have oxidative, then they would happily be oxidized further. How exactly? This becomes propanoic acid. This is R. Huh? And this becomes benzoic acid or benzene carboxylic acid. This is benzene carboxylic acid, aka, or also called, in short, benzoic acid. Benzoic acid is the common name, and benzene carboxylic acids, my dear, this is the IUPAC name. An alkene A on ozonolysis gives a mixture of ethanol, okay, ethanol, and pentane 3-one, okay. Write the structure and IUPAC name of A. How sweet, how emotional, how stupid actually. All you need to do, my dears, is just to combine back this double bond, this one. Take back these oxygens and just merge them back. A very simple trick this is. And what you get is the correct answer. So all I need to do is, this O is gone and double bonds join. Yes, that is the trick, and you get it straight. Oh wow, that's the answer. Yes, that's the answer. This is the alkene A, which on ozonolysis gives you a mixture of ethanol and pentanone. Write the structure. We have written the structure. Write the IUPAC name. Let's write down the name. That's not a big deal. 1, 2, 3, 4, 5. So this is 3-ethyl pent-2-ene. 3-ethyl pent-2-ene. That's all. An alkene A contains 3 CC, okay, 8 CH sigma bonds and 1 CC pi bond, okay. A on ozonolysis gives 2 moles of an aldehyde of molar mass 44. Write the IUPAC name of A. There could be 2 ways of doing this. One way, you could just read the first line and figure out the formula from there and then solve the rest of it. That is one method of doing it. The second is, go by the second half. A on ozonolysis gives 2 moles of an aldehyde. So I have 2 moles of an aldehyde of molar mass 44. Now that is very simple. If you have RCHO, this is an aldehyde, and this has a molar mass 44, right? And R, what is R? R is Cn H2n plus 1. Can I find out this molar mass Cn 12n plus 2n plus 1? This is the molar mass of alkyl group. What about aldehyde? Carbon 12, oxygen 16, 28, and this is total 29. Oh my God, how stupid and emotional this is. I have 14n plus 30 is equal to 44. N, if you solve it, it just comes out to be 1 directly. What does it mean? It simply means that this is CH3CHO. Oh, this is just acetaldehyde. Yes, this is just acetaldehyde. And then suddenly I get the brain wave. How about joining 2 acetaldehydes? If I join just 2 acetaldehydes like this, if I just join them back, what do I get? Well, I get just this. This looks like alkene. 2 moles indeed. But does this condition satisfy what we had there? It contains 3 carbon-carbon bonds. 1, 2, 3 bonds. Yes. 8 CH sigma bonds and 1 pi bond. There is 1 pi bond. 1, 2, 3, 4, 5, 6, 7, 8. Yes, there we are. So what we had is 2 butene. So this compound A which we are talking about actually is 2 butene. Propanol and pentane-3-one are the ozonolysis products of an alkene. Okay, what is the structural formula of the alkene? Let's work that out. Propanol and pentane-3-one. This is what they are. And if you just look at the trick of combining them back, what would that be? Well, that is simply, you take this portion and just merge it. Remove the double bonds, remove the oxygen atoms and join the double bond, and it looks like you get what you need. This. Oh, sorry, I just made a silly mistake. Yups. This portion is this, and the top portion comes from here. Just check. Got it? And we just make a linking double bond. I'll just erase out the dirty parts so that you can get a clear-cut view of what the actual molecule is. This is the structural formula of alkene. They have not even asked for a name, so why bother giving a name? This is the answer, and that's it. Write the chemical equations for the combustion reaction of the following hydrocarbons. butane C4H10. All hydrocarbons burn to give CO2 and H2. Well, 4 plus, sorry, this is 8 plus 5, 13, so this is 13 by 2. This is the balanced chemical equation. Pentene is C5H10. Ten plus 5, 15 oxygens, so 15 by 2 O2. All organic compounds burn to give CO2 and H2O. So these are simple, very simple combustion reactions. And equations, hexane. Hexane is C6H10. 2N12 minus 2. 2N minus 2. That is hexane. Let's burn it. You get 6 CO2. Funny enough, you always are getting 5H2O. 12 plus 5, 17 by 2O2. And then you have the loveliest of all, toluene. What is toluene? This is our lovely toluene. What is the formula? This is C7H8. Let's burn it. Yes, 7 CO2 plus 4 H2O. That makes it 9 O2 in case you choose to burn it like this. Draw the cis and trans structures of hex-2-ene. Lovely. Which isomer will have higher boiling point and why? Let's see. First of all, let's draw the double bond. Hex-2-ene. So this is 1, 2, 3. Now, 4, 5, 6. 1, 2, 3, 4, 5, 6. And 1, 2, 3, 4, 5, 6. This is cis and this is trans. So cis and trans structures, I hope you can see very clearly. And if you still can't figure out why cis or why trans, let me help you out. You could have pointed it out like this. See. Double bond, both the alkyl groups are on the same side and both the alkyl groups are on the opposite side. Double bond, opposite sides, trans. Double bond, same side, cis. Okay. What about higher boiling point? For that you should worry about the dipole moment. See, this has a certain dipole moment. Oh my God, this is... See, this has a certain dipole moment. Alkyl groups release electrons in this direction and in this direction. So overall it has a dipole moment, net dipole moment in this direction. This has in this and this one has in this direction. So they tend to cancel out. So overall, one thing you can say for sure, that dipole moment mu for cis is more than trans, because the dipole moment, because of both the alkyl group, tends to add up in the case of cis and it tends to cancel in the case of trans. If the dipole moment of cis is higher, this means intermolecular forces of attraction is higher for cis as compared to trans. And if more is the attraction, then my dears, more is the boiling point. Therefore, boiling point of cis is more than boiling point of trans. As simple as this. Why is benzene extraordinarily stable, though it contains 3 double bonds? Benzene, dears, has a very special property. Although it has 3 pi bonds and these pi bonds are supposed to be unstable because Pi bonds are supposed to be reactive. They should jump up and down, react, and give Bayes reagent test, and etc. etc. They do nothing of that kind. Why? Because benzene gets some very weird extra stability, and this extra stability, dears, pertains to a phenomenon called aromaticity. What exactly is aromaticity? So first of all, why is benzene more stable? This is because benzene becomes aromatic. And what is the meaning of aromaticity? It means that if you take a benzene molecule, right, let us take it, and if you observe the p orbitals, if you observe the p orbitals within benzene molecule, the unhybridized p orbitals, you would find that they overlap in such a way that electrons can go round and round and round in them. What? Yes. Electrons can actually, and since a circle has no end, electrons can keep rotating in them forever. And this suddenly makes the entire affair very stable. Why? Because electrons love to move around, and if they get extra space to move in, they feel very happy and very stabilized. So, why is benzene extraordinarily stable? Though it contains 3 double bonds. So what is the answer I'll write? I'll say, number 1, benzene is aromatic. In one word, this is the answer. Because it is aromatic, it becomes more stable. Now, if somebody asks you, why? If the question is, say, more than 1 marks, and if they ask you to explain why aromaticity is more stable, then you say, let us look at the structure of benzene. Each carbon of benzene, first point, each carbon of benzene has 1 unhybridized p orbital. Second point, all these p orbitals are parallel to each other and overlap. Third point, because of these overlaps, electrons present within, there are 3 pi bonds, right? So there are 6 pi electrons. Electrons can actually move in circles within the benzene ring. They are delocalized over all the 6 atoms. They can move around, and this delocalization improves the stability, or makes this very, very extra stable. And this is the beauty which makes benzene extraordinarily stable. What are the necessary conditions for any system to become aromatic? Well, there are, interestingly, 3 or 4 conditions. First, the system must be cyclic. There has to be a ring. Open chain systems cannot become aromatic. Sorry. The system has to be cyclic. Then each member of, each atom of the ring must contain at least 1 unhybridized p orbital. That means it can never be sp3. A corollary of this is, this means never sp3. It is usually sp2, and in rare cases it may even be sp, but it is never sp3. Fine. Anything else? Yes, yes. Third point, ring must be planar. Must be planar, which implies all these p orbitals, these the ones which are mentioned in point 2, must be parallel and conjugated. Now, the students are very confused by such things. They say, how do we are not able to see the molecules, how do we know this? Very simple. If the molecule is planar, if the ring portion of the molecule is planar, automatically all these unhybridized p orbitals would become parallel and they would become conjugated. You don't have to worry about this. But what is the reason? I have given you, what is the importance of being planar? If the ring is planar, only then will all these p orbitals be parallel, only then they will be conjugated, and only then will the system be aromatic. So that is why I have said this is Important. And fourth, Huckel's rule. A very cute scientist called Huckel, a little stammery person. Huckel said that there must be, see, the number of electrons in the ring must be 4n plus 2. 4n plus 2 pi electrons are a must, where n can be 1, 2, 3, 0 also for that matter. So you can have 2 pi electrons, acceptable. You may have 6, you may have 10, you may have 14, you may have 18, but you cannot have 4, 8, multiples of 4 you cannot have, you can't have odd number. So the number of pi electrons in the ring must be 4n plus 2, where n may be 0, 1, 2, 3, 4, whole number, any whole number for that matter. Right? If all these 4 conditions are satisfied, there are essential 4 conditions. If all these 4 conditions are satisfied, then the molecule becomes aromatic. Explain why the following systems are not aromatic. Well, look at this. Within the ring, the moment you have an sp3 atom, it will never be aromatic. So in 1 and 2, the obvious sin is the presence of an sp3 hybrid atom in the ring. In such a case, the system becomes non-aromatic. 1,3,5,7 cyclooctatetraene, a very rare and funny case. If you see N, is there a ring? Yes. Are all the atoms sp2 hybridized? Yes. But then there is a problem. Number of pi electrons is 2, 2, 2, 2. 2 plus 2 plus 2 plus 2. 8 pi electrons. Now, this does not fit in 4n plus 2 formula. So, Huckel declared very clearly that this is bad, 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 and this is not going to be aromatic because it does not satisfy Huckel's rule. As a matter of fact, it is anti-aromatic. What? Yes, like aromaticity attracts extra stability, anti-aromaticity attracts extra instability. What the hell? This is a beautiful world. If you have, if you have gods, you have demons. If you have day, you have night. If you have good, you have bad. Same fashion, if you have aromaticity, you also have anti-aromaticity. Aromaticity tends to make things more stable. In the same fashion, anti-aromaticity tends to make things more unstable. That is ugly. It is positively ugly, but that is the way it is. So let's take a further look. It does not fit in 4n plus 2. Yes, no doubt. Now, so actually, cyclooctatetraene would have become anti-aromatic and very unstable. Whenever you have 4n plus 2 pi electrons, it is aromatic. And whenever you have only 4n, if you have only 4n, then it becomes anti-aromatic. Oh my God, so this must be really bad. Yes, it is bad. But something very funny happens, Cyclooctatetraene, it becomes a tub-shaped molecule like this. What? Yeah. This is front, that is back. Don't get confused. Like this. So what happens is the molecule bends, it moves out of plane so that it can avoid anti-aromaticity. The moment it is not planar, it is neither aromatic nor anti-aromatic, it is simply non-aromatic. And cyclooctatetraene, because of this shape, becomes non-aromatic. Everybody wants to become aromatic, so they adjust themselves to become aromatic. And everybody wants to avoid anti-aromaticity, so they move out of plane so that they don't become anti-aromatic. How will you convert benzene into para-nitrobromobenzene? Well, I have benzene and I wish to convert this into para-bromonitrobenzene. So there are two substituents, bromo and nitro. How should I do this? If I do nitration first and attach nitro group, please remember, number one, benzene ring gets deactivated, and number two, nitro group is a meta-directing group. So no, I can't nitrate first, I must brominate first. So Fe, Br3 and bromine electrophilic aromatic substitution, I get bromobenzene. And once I have bromobenzene, bromo is an ortho-para-directing group. I carry out nitration, concentrated HNO3 plus concentrated H2SO4, the standard classical nitrating mixture. And I get para, plus I also get some tiny bit of ortho-nitrobenzene also, because bromine is an ortho-para-directing group. And then I can separate by fractional distillation. Very easily they can get separated, and I would get para-bromo nitrobenzene. What about meta-nitrochlorobenzene? The answer is very simple. How do I do it? Should I do chlorination? No. Chlorine is an ortho-para-directing group, so never even think of that. You should take a meta-directing group. And which one is meta-directing? Nitro group is meta-directing. So you take concentrated H2SO4 plus concentrated HNO3. Wow. And what would you get? You get nitrobenzene. Nitrobenzene, yes. And then you carry out chlorination. Since nitro is a deactivated group, it will be difficult to make it react, but ultimately it will, and you will get metachloronitrobenzene, because nitro is anyways a meta-directing group. Benzene is to be converted into para-nitrotoluene. Oh wow, how do we do that? Para. Now nitro is a meta-directing group, so we can never dream of actually first nitrating it. First, just make toluene. In very limited quantity, you take excess benzene and you get toluene, right? And once you have toluene, concentrated H2SO4 plus concentrated HNO3, the so-called nitrating mixture, methyl is ortho-para-directing group, but it is also a bulky group. So major product is going to be para, and a very small quantity of ortho will be there. You can separate that by fractional distillation, and this is how you get para-nitrotoluene. Somebody wants to convert benzene into acetophenone. Wow. Now, if you want to convert benzene into what is popularly called acetophenone, the group is CH3CO. You should use acetyl chloride with AlCl3, the classic Friedel-Crafts acylation. One step, direct, and you get acetophenone. In the alkane, ting-tang, identify primary, secondary, tertiary carbon atoms and give the number of hydrogen atoms bonded to each one of these. First, let us draw it properly. I have CH3, CH2, C, CH3, CH3, CH2, CH, CH3, and CH3. We have to identify primary, secondary, tertiary. This is primary. Carbon attached to only one carbon is called primary. This carbon is attached to two carbons, so this is secondary. Primary, primary. Let me just write down primary by black. Yes, I think let's color code it, it would look more beautiful. Primary it is. And then let me use blue for secondary. Secondary, secondary. Oh, I just have two secondaries. And then I also have tertiaries. Purple for tertiary, tertiary. And there is one more remaining. This is actually quaternary. Quaternary means a carbon atom attached to 4 different carbon atoms. Wow. we have identified the number of hydrogen atoms. So hydrogen atoms bound to primary carbon are called primary hydrogen. Similar ways, you have secondary and tertiary hydrogen atoms. There is there is nothing called as quaternary hydrogen because there is no scope left for hydrogens here. Tertiary hydrogen is only one. Oh, that is so sad. Sad or bad, it is just one. Secondary, one and two secondary atoms. Yes, indeed. So I have four secondary hydrogens. Okay, and what about primary? 3, 3, 3, 9, 3, 3, 15. Fanciful. I have 15. My God, I have 15 primary hydrogens, 4 secondary, and 1 tertiary, and 0 quaternary. Obviously, I have 20 hydrogen atoms. Have I counted correctly? Should I cross check? We should. How many carbon atoms are there? 1, 2, 3, 4, 5, 6, 7, 8, 9. 3 plus 3 plus 3, 9. So we have C9. H2N plus 2. C9, H20. Hydrogens should have been 20 and they are coming out to be 20. So yes, we have not missed out on anything. It is correct. We have cross-checked also. And that's it. What effect does branching of an alkane chain has on its boiling point? Well, as branching increases, surface area of the molecule decreases. As branching increases, surface area of molecule decreases. Therefore, the forces of interaction. See, if I have more surface area of hands like this, in winter season, if I rub my hands, I generate warmth, right? Do I do it like this? No, that's very stupid. Yes, because this surface area is less. If I rub them, I will get much lesser heat because interaction is less, right? So, surface area of molecule decreases. Therefore, less forces of attraction. Why less forces? These are what? These are London forces, or sometimes called dispersion forces. So dispersion forces decrease, so lower boiling point. So as branching increases, boiling point decreases. Look at a classic example. Pentane is a boiling point of 36.1 degrees Celsius, while neopentane, which much more branching, comes down to barely 9.5 degrees Celsius. Why? Branching increases, surface area decreases, dispersion forces decrease, and boiling point also decreases. Addition of HBr to propene yields 2 bromopropane. Okay? While in the presence of benzoyl peroxide, the same reaction yields 1 bromopropane. Explain and give mechanism. Well, let's see what is happening here. Addition of HBr to propene yields 2 bromopropane. This is propene. You add HBr. Mechanistically, what happens? First of all, H plus gets added. And as H plus gets added, what do you get? If H adds here, you get secondary carbocation. Or there is another possibility. H adds up here, so you have primary carbocation, and this is less stable. And this is more stable. Yes. So what happens is in step 2, let me come to step 2. If you add Br minus, I get this as major product. Why? Because this is more stable. And I'll get this as minor product because this is less stable. This is the reason for obtaining 2 bromopropane. 2 bromopropane when HBr is added to propene due to electrophilic addition reaction. This is the mechanism for electrophilic addition, right? But in the presence of benzoyl peroxide, now what is benzoyl peroxide? It is pH COOO-CO-pH. What is this? This is benzoyl peroxide. Wow. And what happens? What happens is it just breaks up. I get pH COO radical like this. Is it a free radical? Yes, it's a free radical. And this free radical can react with HBr. And it will generate pH COOH plus Br radical. Fanciful. So benzoyl peroxide is a small initiator in very tiny quantities. It gives you bromine radicals. And once, my dear, we have Br radicals, the fun begins. If you add Br, there are two ways in which it can add. If it adds on carbon number 1, like Br, I get a primary radical which is less stable. And if it adds here, I get secondary radical which is more stable. You understand what is happening? I'll just make you imagine. See, you can imagine the whole thing like this. This is imagination bubble. This is alkene, right? Just imagine it breaks up as two dots. It has two electrons. It breaks up one here. And then if you add one Br here, dot plus dot will make a bond. Yeah. So I get a bond here. I get a bond here like this. So whichever place Br forms a bond on the other carbon, I would simply have an unpaired electron like this. So, and then when HBr comes here, what will happen? This is going to take away one hydrogen, leaving Br radical again. This will take away one hydrogen, leaving Br radical again, and this Br radical will go and jump on some other molecule and again add on that. Now do you see that this is the major product? Why? 1-bromo, anti-Markovnikov product is the major product. Why? Because secondary radical is more stable than primary radical, and in this case secondary radical happens to be the intermediate, while in the first case primary, the ugly primary radical was the reaction intermediate, right? So as per the mechanisms we can see that usually when you just add HBr to propene, it is electrophilic addition. You get 2-bromopropane as the major product. But when you add benzoyl peroxide, the mechanism changes to free radical mechanism. And in that, 1-bromopropane becomes the major product. Write down the products of ozonolysis of 1,2-dimethyl benzene, that is O-xylene. Okay. How do the results support Kekulé structures for benzene? Well, the fun part is, if you just look at Kekulé structures, these will be these two and these. And very interestingly, if you ozonolyze benzene, you would discover that you get the actual products as the breakup structures of each of these. What does it mean? If this happens to be the structure, I would obtain please note these two are same. So I will obtain 1, 2, 3. This is 2-oxopropanal, that is, and glyoxal. There are two products like this. This is repeated, this is. What about them? In this case, very funny, you would obtain 2 moles of glyoxal like this. you'll obtain glycol again. In addition, you would obtain butane dione. Actually, when you ozonolize 1,2-dimethylbenzene or O-xylene, you obtain not 2 but 3 different products. You obtain glycol, you obtain 2-oxopropanol, and you also obtain butane dione, which is a kind of proof. Why? Because if you take these of 2 calculus structures, there are 2 different structures, and if you ozonolize, only one structure would give you only 2 products. The other structure would give you again only 2 products. But in actuality, you obtain all 3, which is a kind of proof that actually both these structures must be valid, they must be true, and then only you would be able to obtain 3 different structures like this as ozonolysis products. Arrange benzene and hexane and ethane in decreasing order of acidic behavior. Wow. Also give a reason for this behavior. Let's do that. Well, let us say benzene becomes acidic. 1, 2, 3, 4, 5, 6. And hexane becomes acidic. And ethane, HC, they become acidic. What is the meaning of becoming acidic? Becoming acidic means that they are able to release H+. And if this releases H+, let me make conjugate bases. If they lose H+, what do I get? I get HC triple bond C minus. I get CH2 minus. And I get phenylalanine like this. Most stable of 1, 2, and 3 is 3. 3 is most stable, most easily formed. The reason being that the orbitals in which they are lying, this is sp hybrid orbital, this is sp2 hybrid orbital, and this is sp3 hybrid orbital. More the s character, higher is the electronegativity, greater is the capacity to maintain or to be able to keep electrons with itself, and greater is the stability of carbanion. So please note, an sp2 or sp3 orbital, I'll just draw a small chart. sp orbital has 50% s character. sp2 has 33.33%. and sp3 has only 25% s character. And greater the percentage, this is 50, don't get confused. Greater the percentage of s character, more is the electronegativity. More is the electronegativity, more is the capacity to keep lone pair with itself. That means more stable is the carbanion in sp hybrid orbital than in sp2 and than in sp3. More is the stability of carbanion, that means this is formed more easily. If this is formed more easily, it means this can release H+ more easily. That means this is more acidic. So 3, acetylene is most acidic. Ethane is most acidic, and then comes benzene, and least acidic. This is acidic character. So you can say, greater the stability of conjugate base, greater is the acidity of conjugate acid. Same is the order of stability of conjugate bases, and same is the order of stability of, order of acidity of conjugate acids. Why does benzene undergo electrophilic substitution reactions easily and nucleophilic substitutions with difficulty? There are 2 portions in this question. First of all, electrophilic substitution easily. Electrophilic means electron loving, and the benzene ring contains above itself and below itself a very nice happy pi electron cloud. It has 6 pi electrons. It is rich, and these electrons are just happily rotating up above and below the ring. They serve as a very good source of electrons, and that is why it can easily undergo electrophilic substitution. Why? It is electron rich. It shows off electrons, and people who love electrons come to it. Electrophilic reactions become easy. That is the first part. Then, nucleophilic substitutions are difficult. Why? You have to appreciate that typically nucleophilic reactions happen by SN1 or SN2 mechanisms. In SN1, you get a carbocation. Now, phenylcation is most unstable. So, benzene ring absolutely hates the generation of phenylcation. Since it does not make phenylcation easily, SN1 reactions are very rare. What about the second possibility of SN2? SN2 is also possible. But again, there is a problem. The problem is of backside attack. SN2, in classical SN2, what happens is, if you have a leaving group, exactly from the opposite side, there has to be an attack. Unfortunately, on the opposite side, there is an entire molecule. So unless you destroy the molecule itself, you can't have a backside attack in case of SN2 mechanism. There is also additional problem that in both of these cases, sp2 hybrid carbon has stronger bonds with leaving group. The bonding with leaving group is very powerful. It is difficult to break. So if you feel that you should throw away the leaving group first, that thing is not possible. It's very difficult. And that is why nucleophilic substitutions are an absolute rarity in case of benzene. Although, since it is electron rich, electrophilic substitutions prevail. They happen very easily. How would you convert the compounds into benzene? Ethyne. Ethyne, very simple. Red hot iron tubes, 30 to 50 atmosphere pressure. Sometimes people use copper tubes also, which is fine. And ethyne trimerizes into benzene. That's it. How do you convert ethene to benzene? Now, ethene to benzene is not as straightforward as acetylene to benzene. Why? Ethyne, you just pass into red hot iron cubes, apply high pressure, high temperature, and it polymerizes, it trimerizes to give you benzene. Now, if there is a method by which you could convert ethene to ethyne, then that would be phenomenal, because ethene gives you, say, ethyne, and ethyne, you have 873 Kelvin catalyst, high pressure, and you can trimerize to get benzene. This is something which we are already aware. Ethene to ethyne is a little more interesting. How shall we do that? Well, there could be many ways. One method could be add chlorine. So you will have 1,2 dichloroethane. Chlorine NCCl4 or any inert solvent, you add electrophilic addition and you get 1,2 dichloroethane. Then use alcoholic KOH. H and Cl would be eliminated and you would get, well, vinyl benzene. This is dehydrohalogenation. And as if that is not sufficient, add NaNH2. Solvent is liquid ammonia. Now this is a much stronger base. And this is a base which can remove the remaining H and Cl. Vinyl chloride can also be dehydrohalogenated to acetylene. Wow. So 1, 2, 3 steps, yes. And then this acetylene on trimerization can give you benzene. Wow, there are 4 steps. Yes, there are 4 steps, but this is how you can very happily get benzene. Hexane to benzene. Is there a method? Yes. There is something called as cyclization and aromatization. You have Al2O3, Cr2O3 catalyst, 550 degrees Celsius. You pass it over and apply some pressure also. You find that it's a destructive reaction. It's not very easy. But then on passing over alumina catalyst at high temperature, there's a reaction called cyclization and aromatization. It becomes cyclic, it loses hydrogens, and you get benzene directly. Poor yields, but yes, it is one shot direct, and you can get that. Write the structure of all the alkenes which on hydrogenation give 2-methyl butane. That's lovely. 2-methyl butane is this. This is 2-methyl butane. How many alkenes can actually offer us this luxury? Well, let me just draw different possible alkenes and check. If this is an alkene, on hydrogenation, this pi bond will be removed and I would get this. The structure would remain the same. Yes. This is a second alkene which can give me that. Yes. And this is a third alkene which can give me that. And somebody might say this is the fourth alkene. Unfortunately, the answer would be no. Why? Because they are same. What a shame. They are the same. Yes, they are the same. So, you just don't have to count this. 1, 2, and 3. These are the 3 structures of 3 alkenes, which on hydrogenation can give you 2-methyl butane. Arrange the following set of compounds in order of their decreasing relative reactivity with an electrophile E+. How quickly would somebody react with an electrophile E+? It depends upon, if it is very electron rich, it will react more quickly. And if it gives away its electrons more easily, then also it would be more quick. Let's take a look. We have chlorobenzene, fine. And we have 2,4 dinitrochlorobenzene. Oh my God. And then we have para-nitrochlorobenzene. This is as easy as it gets. First of all, please appreciate that NO2 is a very strong electron withdrawing group. Chloro itself is an electron withdrawing group, but see, please note that chlorobenzene happens to be the same in all these cases. If you just look at this portion, chlorobenzene. It is the same chlorobenzene here. It is the same chlorobenzene here. It is the same chlorobenzene here also. There is no difference in chlorobenzene. The only difference, my dear, lies in nitro. There are 2 nitro groups and there is 1 nitro group, and here there is no nitro group. And NO2 is an electron withdrawing group. EWG, electron withdrawing group. It decreases the electron density within the benzene ring. And that is why you find if you have 1, 2, and 3, 1 would be fastest. Then comes 3, which has only 1 nitro group. And poorest is 2, which has 2 nitro groups. Since they withdraw electrons away from benzene ring, they make benzene ring electron deficient. And electrophiles will approach a ring which is electron rich. So since they do the opposite, they decrease the reactivity. You have second example. You have a lovely toluene, beautiful electron rich benzene ring and slightly electron releasing methyl group, lovely as they are. We have same toluene, but now there is a villain. Who's the villain? The villain is a nitro group. The villain is a nitro group. Okay? Nitro. 1 nitro or 2 nitro groups. What exactly happens? What happens with these nitro groups is that they withdraw electrons away, and when they withdraw electrons away from benzene ring becomes electron deficient, and as the benzene ring becomes electron deficient, you find that its reactivity with electrophiles decreases. So this is the order of decreasing reactivity with electrophile E+. Yes, it is. Out of benzene, meta-dinitrobenzene, okay, and toluene, meta-dinitrobenzene. My God, 2,2NO2 groups, very heavy. Heavy means they're tremendously electron withdrawing groups. They make the ring very electron deficient. And toluene has methyl group, which is slightly electron releasing group. These are electron withdrawing groups. Which will undergo nitration most easily and why? Toluene. Benzene is the reference. Two nitro groups make it very poor for electrophilic aromatic substitution, and methyl has released electrons that has made a benzene ring more activated, more electron rich towards attracting an electrophile. That means undergoing electrophilic aromatic substitution. This is good. Yes, this is good. So toluene, the answer is toluene, the third one, will undergo electrophilic aromatic substitution most easily. The reason being, CH3 group is a plus I and plus H group. It shows inductive effect. It also shows hyperconjugation. And because of these, it releases electrons, extra electrons within the benzene ring. It makes benzene ring relatively more electron rich. And since the ring is richer, it can more easily attract electrophiles, and more quickly it can undergo electrophilic aromatic substitution. That's why. Suggest the name of a Lewis acid other than anhydrous AlCl3, which can be used during ethylation of benzene. Let's first see what is ethylation of benzene. Ethylation of benzene is when you attach an ethyl group to benzene. And this can be done if you have C2H5Cl. This is the regular reaction, right? You can also use something funny. What? You could have used C2H5Br and anhydrous AlBr3. Can we use this? Yes. Or you could have used BCl3 or BF3 or BBr3 or in this case FeCl3, all anhydrous. In this case FeBr3. All these are excellent Lewis acids, and any one of them would have done the job as easily as AlCl3. Why is Wood's reaction not preferred for preparation of alkanes containing odd number of carbon atoms? Illustrate your answer by taking one example. Let's take the most general example. Let us take any alkane. Any alkane is CnH2n plus 1 H. This is alkane, right? And let's say we have an alkyl halide made of this. An alkyl halide would have the formula X here, X. The moment you carry out Wood's reaction, that means you are adding sodium. This reacts away. You have dry ether as the solvent. Very good. You have sodium halide. Excellent. And you have CnH2n plus 1 bonded to CnH2n plus 1. So essentially, you have C2n H4n plus 2. This is the product which is obtained. As you can very genuinely see, any number, now n could have been any number 1, 2, 3, 4, 5, 6, 7, 8, 9. If n can be any number, and if you multiply that number by 2, you always get an even number. So, we normally tend to get, in case you have only one alkyl halide, you will surely get an alkane which contains even number of carbon atoms, right? Now, somebody jumps around and says, no, I will find odd. How? Let's take an example of, say, n is equal to 3. The easiest is n is equal to 3. And let's say somebody says that I am going to take methyl chloride and ethyl chloride and I am going to mix them and make propane. You're most welcome, you can try. Now, somebody imagines, see this. They'll say, I'll do this and I'll get CH3 CH2, CH3. Odd number, 3. One can feel very happy and very smart that they have done that. But then there is a problem. You just don't have one molecule of ethane and methane. You have actually millions into millions into millions into millions into millions of molecules. Yes. So what happens is actually this. What you can't stop is there would be equal probability of this reaction happening, which will give you, and there will be C2H5Cl This is, my dear, what you are going to get. So, you get butane, you get ethane, and you get propane. So, if you have Rx and R-X, and if you mix them, you will get actually RR dash. Yes, you will get some amount, but unfortunately, you get equal amounts of RR and R dash R dash. So whatever you wanted is never more than 1/3, which is really bad. And that is why Bode's reaction is definitely a bad idea in case you want alkanes with odd number of carbons only. So dears, these were the solutions of NCERT questions on hydrocarbons unit 13 of standard 11th. I'm Shishir Mittal from Vyas Certification. And in case you want more content of this, especially for IIT JEE or NEET, download the Vyas app today and access whatever material you wish by joining our courses. Have a great time.